Okay, as we mentioned last time, enzymes are proteins. So they're not our metals as we have in organic chemistry. There are enzymes are proteins that act as catalysts. So how does an enzyme act to work to reduce the activation energy? So what it does is it orientates and when you see this word substrate, that's reactant. So whenever you see the word substrate, think word reactant. So what it does is it takes the reactant and sort of strong arms it so it has the right shape and charge distribution, like the transition state. So I think of it as, here's my arms are the enzyme, and it's coming around the substrate, and it sort of grabs the substrate and like twists it or does something to it to make it look like the transition state. And we all know the rate depends on that activation energy. So we can increase the rate of a reaction by 10 to the 20th. We mentioned that if we increase temperature, we can make the rate of a reaction faster. So you can see in this, this plot here, we have activity. So here's 100%. This means that all the enzymes are working. And then the temperature here. So room temperature is about 25. What is body temperature in Celsius? 37. Okay. My mother gave me thermometers in Celsius. So when I was in grad school and I couldn't afford to buy a new thermometer, I had to do the conversion between Celsius and Fahrenheit. That's what you do when you don't have any money. So, okay. When I was sick, I was like, what is it? Do I have a fever or not? So you can see at zero, nothing's really moving. Remember, the kinetic energy, we have our molecules moving. You have to have a collision for reaction to happen so that the substrate has to go into the active site. And so 0 degrees, there's not a lot of movement, and it increases. Now, what I'd like you to do in your notes is sort of like, instead of do a gradual slow down here, draw a straight line down. It doesn't matter what temperature, but draw a straight line down. Why do I say draw a straight line down? What's going to happen at a certain temperature? We're going to denature the protein. We're going to denature the enzyme. So I just wanted to emphasize that there's going to be a temperature at which the protein denatures. It can be sort of gradual where we denature some but not all. But I want to make that sort of impact on you that it is going to be denatured at some temperature. So it's dangerous if we increase the temperature to increase the rate. All right, now, we also know that changing the pH can change the tertiary structure of a protein, but we need to keep in mind that not like everyone has their own comfort zone. So we think, oh, we need to be at physiological pH for an enzyme to work. Well, it depends on where it works, right? So amylase in your mouth works at mouth pH, which is, around 7. But where does arginase work? And where does pepsin work? Arginase works where? In the intestine, small intestine, right? And pepsin works where? In the stomach. So in the stomach, you have acidic conditions. So it is going to work optimally at very acidic conditions. Arginase in your small intestine is actually at much higher pH. I don't really know what pH your small intestine is exactly, but it's obviously a much higher pH. So we have an optimum pH for activity for each enzyme, and it depends on where it's working. Now, I'm going to go over briefly naming, just so that you can recognize a molecule, but I'm not going to hold you accountable, except for one thing. But I just want you to know that, and be familiar that there's a numbering system and a systematic two-part name. So just so scientists can, across languages, speak to each other about enzymes, we have a numbering system, a systematic name, and then a common name, just like everything else in chemistry. Chemistry and biology developed over time. They made up names for things as it came along, and then they said, well, now we have to make sense of it. So they came up with a systematic two-part name, and then they said, oh, we have to speak across languages, so let's come up with a numbering system. So we know alcohol dehydrogenase as alcohol dehydrogenase. But if the systematic two-part name is alcohol ... NAD oxidoreductase. So what it's doing is it's involved in a redox reaction with alcohol. It has a numbering system, and so the systematic name gives more of a clue of what the enzyme does. So that's why I like that. But no one uses it. I've never heard anybody calling an enzyme by this systematic two-part name. Even when we're going over our pathways, never will I use the systematic two-part name. We always use the common name. The one thing I do want you to know about the naming is, see this ASE? That's the ending for our enzymes. So that's it from this slide. But, I mean, be familiar. But there are basically two, oops, hold on. I'm missing something. There's 6 major classes of enzymes based upon what they do. So just like the name says, oxidoreductases catalyzes redox reactions or electron transfer reactions. You'll see reductases, peroxidases in the names. Transferases transfer. So that's not too bad, a group from one molecule to another. You'll see transaminases. That one will transfer an amine group. Transcarboxylases, that will transfer a carboxyl group. Hydrolases will cleave bonds by adding water across the bond. Lyases remove groups to form double bonds. You'll see synthases or decarboxylases. Isomerases isomerize. So that's not too bad. You'll see mutase a lot when we're doing this. Mutases will be what we see. And ligases bring two molecules together. Now, so synthetases remove groups, then synthetases bring two molecules together. So I'm not going to test you on the difference between those two. I just want to point out to you that there's definite jobs that our enzymes have, and these are the jobs that they do. Okay. Kinetics. So I'm assuming that all of you have had Chem 2 in the past 5 years. And if you have not, then this might be a little bit more of a shock to you than others. And if you find this difficult, I can give you lots and lots of resources to help you out. But just take it slow and bear with me. But we're going to review kinetics because we are going to study kinetics for our enzymes. So enzymes, of course, speed up rate. Rate has to do with kinetics. So let's take this reaction. Molecule A reacts with molecule B to produce our product P. And so when we say we have the rate of the reaction, we say the rate is the disappearance of our A over time, the disappearance of B over time, or the production of our product over time. All right, so I want to define some things before I go forward. Delta means final minus initial. All right, so we're always going to take the last minus the front. So that's why we have this negative in front of our reactants, because the reactants will be disappearing. We're not going to have a negative rate. So we are disappearing in our reactants, but then creating our products. We also have our rate law that will tell us more about the mechanism of our reaction. So the rate is equal to some constant times the concentration of our reactants raised to some power. F and G I just chose. How do you determine F and G, guys? How do you determine F and G? Are you going to look at the coefficients in your reaction? No. What are you going to do? What do you have to do? You have to do an experiment. Yeah, it has to be experimentally determined. And so we're going to do that. Remember, if you took Chem 2 recently, there was either a graphical method or an initial rates method. You remember that? Am I making people's heads hurt? It's too early on a Monday morning for this. So we're going to look at the initial rates method. But here, the K is a proportionality constant. It's a rate constant. And then we say the order of the reaction is the sum of these exponents, F and G, and we can call it a reaction a certain order. So if this was both 1 and 1, if F and G were both 1, then we would say it would be first order with respect to A, first order with respect to B, and then the reaction would be overall second order. That's right. So and what these orders have to do is what's bouncing into what. So if it's first order, it needs to be present for the rate to increase or decrease. But if it's second order, you have to have it bumping into itself before it bumps into something else. So it needs 2 bumps of it. So think of these orders as bumps. So if it's just first order, it just has to be present. But if it's second order, there has to be a collision. So second order overall, that means that A has to collide with B in order for the reaction to occur. If F was 2, then A would have to collide with A and then with B in order for the reaction to occur. And then it will be third order overall. Am I jogging people's memory?
Can you say that again?
Sure.
Sorry.
No, that's all right. Let's start from the beginning. If F was 1 and G was 1, then we would say that the reaction would be first order with respect to A and first order with respect to B, and the reaction overall would be second order. If something is first order, okay, first order with respect to A, what does that mean? It means that it has to be present in order for the rate to increase. So if we increase the concentration of A, the reaction rate is going to increase. That means that A has to participate in the reaction. There's a bump with A. If we said that this was second order with respect to A and only first order with respect to B, then what would happen, most likely, not definitely, but that A would have to bump in with A and then bump into B in order for the reaction to occur. So second order means that there's an additional bump. So think about these orders as bumps. So let's look at a different reaction. Again, here for the reactants, we found experimentally that it's first order with respect to A and first order with respect to B, and the reaction is second order overall. Okay, I got to tell a story.
So you're saying A has to bump into B for second order overall?
For second order overall, A has to bump into B. If, say, it was 0 order with respect to B, then we would assume that it was just A. Okay, that was needed for the reaction rate to increase.
And then you said third order, A bumps into A, then bumps into B.
Yeah, but it would have to be, the 2 would have to be on the A. So if we had a 2 on the B, then B would bump into B before A. So think of the orders as telling you something about the bumps.
Okay.
Now, this seems kind of silly and easy. And we're explaining it very basically. But I used kinetics in graduate school when I was looking at the binding of the anti-cancer drugs to tubulin. Now, I wasn't talking about enzymes in grad school, but I was talking about looking at the mechanism. And all of the anti-cancer drug work that I had done was all on, and I think I may have mentioned it, on tubulin obtained from cow brain. And so all of the looking at the mechanisms of the binding was based on these drugs binding to cow brain. What I was doing is looking at the kinetics of the binding of the same drugs, but to tubulin from different tissues. And I found that there was a different order. I did some experiments, looked at the initial rate, and saw that the order was slightly different. And what that told me and my colleagues is that the mechanism of binding, because the order was slightly different, it was very complex, but because the order was slightly different, that the mechanism of binding was slightly different. And that all of these modeling experiments that we had done on cow brain tubulin might need to be looked at a little bit closer based on what tissues these drugs were binding to. So one of the drugs I was looking at was Taxol. And Taxol is a very common anti-cancer drug now. And the binding of it to cow brain tubulin and the binding to, I isolated a prostate cancer cell tubulin. I found the binding kinetics to be different. Now that's very behind-the-scenes work, but it caused some concern in my group. So there's definitely some higher level concerns and reasons to use kinetic studies. And the end game for our kinetic studies is to look at the mechanism of what's going on in your reaction. So let's take a look at how are we going to get them. What we do is a number of reactions. So here, let's take a look at this reaction where we have diglycine. So it's two glycine amino acids in a peptide joined together by a peptide bond, and we're going to hydrolyze them. It means break apart with water to get two glycines. And what they did is 3 experiments. And remember that these brackets mean molar concentration. So I know this is just to pretend the molar concentration of water. What's the molar concentration of water in water? Does anybody know? It's 55.5 molar, so it's pretty high. So this is kind of weird. We must have done it in an organic environment. But let's just go with it, guys. So the way we determine the order, okay, of the reaction, what is going to be this exponent on the diglycine? So this di, G, is this molecule right here, and then water here. So what is the exponents on the X and the Y? So what we do is we do a number of experiments. We do 2 experiments where we hold the concentration of one of the reactants constant. And what we will do is, say, double the concentration of the other one. And so it's sort of like putting not looking at the water. And we see what happens to the rate. So water is constant, and diglycine is doubled. What's happening to the rate? It's doubling. So what would you say the order is for the X, the diglycine? It would be 1. Okay, I'm sorry, the arrows are not. It's these 2 right here. So this is the one, the animation's not correct. So here, these are the ones that you're going to take a look at to get X is 1. If the rate increases by the same factor that you've increased the concentration, then the order is 1. If we doubled the concentration but quadrupled the rate, then that would be a second order. Yes? Sure. Yeah, for those of you that have not had Chem 2 in a while, and I'm talking about like longer than just last semester, this is going to be challenging. So take a look at the A and B. Okay? What's the difference between A and B? We're just doubling the diglycine. And what's happening to the rate? We're doubling it. So if you, whatever, let me go back. If you double the concentration and the rate doubles, then the order is 1. If you double the concentration and the rate quadruples, then the order is 2. So we're doubling the concentration, we're doubling the rate, the order is going to be 1. So it's changing by the same factor. So if the rate changes by the same factor, you're changing the concentration, then the order is going to be 1. Can we say that again? No? Okay. Anybody else? Yeah. Yes?
So you go from comparing perhaps maybe like the first and the second reaction, A and B, and then A and C after that?
Yeah, I haven't gotten there yet. Yes, we're going to go there. So we're just focusing on the X right now. So we're just taking a look at these two, A and B. Water constant. So it's like we're not paying attention to water. We're taking water out of it. And when you take Chem 2, we go into a more mathematical way to look at it. But we're just looking at it simply. So here, we're taking water out of the story by keeping it constant. Doubling the concentration of diglycine, the rate doubles, so the order is 1. If the rate had quadrupled, then I would say the order would be 2. Most of the time, the order is 1. It's very uncommon to have a reaction where something has to bump into itself before it can react with something else, or it bumps into the other thing and then bumps into itself again. That's an unusual occurrence. Mostly it's one reactant bumping into another reactant.
So the rate quadrupled, then the concentration doubles.
If we doubled the concentration and the rate quadrupled, then the order would be 2. It went up 4-fold, so that it would be the square of whatever you did to the concentration. I can give you guys some reading. Do you guys want me to put up a review of this tonight? Okay, I'll do that. All right, which experiments do we hold the diglycine constant? A and C. So we're going to take a look at A and C to see what the order is for water. So here, the diglycine stays at 0.1 molar, and we're going from 0.1 to 0.2. And what's happening to the rate? It's doubling. So the order for the water is 1 as well. If it had gone up to 4, we would say it would be 2. So what you can conclude about the mechanism is that diglycine has to bump into water for the reaction to occur. Seems like pretty simple, but sometimes it can get a little complicated. And again, I will put up a review of this. I'll try to find something that doesn't go into too much detail, because if you read chapter 13 of the text that we use for general chemistry, it might go into a little bit too much detail than what you need for this. But those of you that have, I'd say within the past 5 years, taken general chemistry and you still have your textbook, go to the kinetics chapter. Okay, let's start applying this to our enzymes. So again, a substrate, that's our word in biochemistry for a reactant. And the active site is the portion of the enzyme that does the work for catalyzing the reaction. And what happens is the substrate gets bound non-covalently, sometimes covalently, to the protein's active site, to the enzyme's active site. And those interactions can be hydrogen bonding, attractions, dipole-dipole. So it can be a lot of different things that bring us there. There can be, and we're going to look at a mechanism in a following chapter where we actually look at what's happening in an active site at the chemistry. But this is one thing that's very important as we go through are, and of course, what do scientists do? They make what are observations in nature, they mathematically model it. That's what we want to do. So what we're going to do is see how they took the interaction between an enzyme and its substrate and mathematically modeled it. And then we're going to see what we do with that model. So one of the foundations for this model is the assumption that we have this enzyme-substrate complex. So when you see E around, that's going to be free enzyme. When you see S, that's free substrate. When you see ES, that's going to be our enzyme-substrate complex. That means that this is bound covalently or non-covalently. The substrate is bound covalently or non-covalently to the enzyme. We have two models to describe, and you may have heard of these before, how this enzyme-substrate complex comes to be. As we've seen or heard, that enzymes are very specific to substrates. They'll pick one molecule but not on the other. And it's based on the shape. But how? Again, there's two models. One, and they sound just like they are. One is lock and key. So the substrate would be the key, and the enzyme would be the lock, and there's an exact complementary fit. This is a nice one to see or to imagine what's happening, but it doesn't always hold water. The more accurate model is the induced fit, where there is a sort of complementary shape between the enzyme's active site and the substrate that's coming in. But what happens is as the substrate's coming in, the active site sort of folds around it. I always think of it like as a fly coming into a Venus flytrap. Isn't that weird? Have you ever seen that? A bug goes into the Venus flytrap and it just closes in around it and digests it alive. So, so I think this is sort of a neat way to think of it, but it's a more accurate way where the substrate comes in, and because of those attractions, it's sort of there's movement of it going around. So here's our lock and key model over here on the left, where you have an enzyme with an active site shape that is exactly complementary to our substrate. But here in our induced fit, it does have sort of a complementary shape to our substrate, but what happens is, in the end, if you notice the end point for the lock and key and the induced fit, they are the same. These are the same picture, here and here, although they look a little different with the enzyme looks a little bit different. But the end is that you have an enzyme-substrate complex. So whatever way it gets there, it gets there. Now, in both models, what happens is, once we have that enzyme-substrate complex, we form our product. The enzyme does its job, and the product no longer has the attractions to that active site. So because it's no longer strongly attracted to the enzyme's active site, it's released. What are we left with? We're left with our product and an enzyme that can be used over and over again. Just like a parking spot. That's why I like to use the parking spots as my little model for what we're doing here. All right, once enzymes have bound the substrate, they work to produce product in one of two ways. And this is what we're going to talk about the rest of today and all through Chapter 7 as well. The two ways are either non-allosteric, which we're going to talk about the rest of today, and then allosteric. Now, what we're going to do is use our reaction orders and our plots of rate versus substrate concentration to notice the difference between the two. Next chapter, chapter 7, we're going to talk about allosteric, non-allosteric, the rest of this chapter. Chymotrypsin is going to be our example of a non-allosteric enzyme. What it does is it cleaves proteins. It chops them up. But it chops them up at the carboxyl end of an aromatic side chain, a side chain that has like a benzene ring in it. And what we see is that low substrate concentrations, the reaction is first order with respect to our substrate. But at higher substrate concentrations, the order changes and approaches zero order. And we see a graph of rate or velocity versus our substrate concentration, and its shape is hyperbolic. All right, let's see. So chymotrypsin basically will catalyze these reactions. It will cleave peptides bonds as well as an ester bonds and bonds next to aromatic rings. And we use this, this reaction actually to help us look at what's going on with the active site. So hold on to this until later, where we're actually going to be looking at what's happening in the active site. I think it's next chapter, what's happening in the active site of our chymotrypsin. But what happens is when it cleaves this bond, this ester bond, it leaves something that's colored. And then we can follow the reaction in the kinetics looking at it using a spectrophotometer, which is always an easy thing to do. Okay, so we're going to spend some time on this one. So here, when we say velocity, think rate. And then here is our substrate concentration. What's going in to the active site? The protein that's going to be chopped up. Now down here, the rate of the reaction depends on the concentration of the substrate. That's what we mean first order, right? But up here, there's so much substrate that the reaction rate does not depend on the substrate concentration. What we said is we've saturated the enzyme. So to understand this plot, what you have to first understand is that we're holding the enzyme concentration constant. So let's say we have 100 chymotrypsin enzyme molecules. What does this shape remind you of? What protein? Myoglobin, right? And myoglobin was one amino acid chain, right? It didn't have subunits, and the same thing with chymotrypsin. It's one amino acid chain. So just like with oxygen in our myoglobin, the same thing happens here with chymotrypsin and the protein that it's going to chop up. So here we have a lot of chymotrypsin free. So when the substrate comes in, it can come in and do its job and leave. No problem. It's like shopping right now at Crossgates. There's no problem. Well, is it open yet? No, it's not open yet. But say we're to go after class, you would have no problem getting in. It will be first order. It would just depend, the rate would just depend on how fast you can work, right? How fast or how long you need to shop, which for me is always way, way too long. I hate shopping, and that's not good with a teenage girl that needs lots of clothes for high school. So anyway, so as we're down here, we have plenty of free. But what's happening as we go up here? What do we say with myoglobin? Why is it slowing down? Yeah, parking spots are getting filled. Our chymotrypsin is getting saturated. So now it's very hard for the substrate to find any free chymotrypsin. So why do we say it's zero order? When something's zero order, if you increase or decrease its concentration, it has no effect on the rate. Do you want me to repeat that, guys? for something to be zero order, when you increase or decrease the concentration, it has no effect on reaction rate.
The concentration of the substrate.
Of the substrate, yeah. So we have a maximum rate at which our 100 chymotrypsins can work. You'll release product only as fast as the chymotrypsin can work to get it done, as fast as the shopping can get done, right? Here, we release product as fast as we can find empty chymotrypsins. But up here, we have to wait for somebody to finish shopping before we can go in there. It works. My shopping thing works. I've used it for years, and I haven't been able to find questions that it doesn't help out with, at least for this. All right, so we have this important term called maximum rate, Vmax. So there's terms that you guys need to remember. Then another one is half of that value. And that half of that value, when we extrapolate down to the x-axis, we get a substrate concentration that is equal to this value Km, Michaelis constant. And we will talk about this later. It's very important. It has to do with the affinity of the enzyme for the substrate. So we'll talk about this one later. Next chapter, we're going to use ATCase. I'm not even going to try to say that. As an example of an allosteric enzyme. It catalyzes the reaction between aspartate and a carbamoyl phosphate. Basically, it's a precursor reaction for the synthesis of our nucleobases. So when this enzyme is working, we see the rate versus the substrate concentration as a sigmoidal plot. I don't need you to remember that what the reaction is that ATCase catalyzes, but I do need you to know that ATCase is our example of an allosteric enzyme. Chymotrypsin is our example of a non-allosteric, and ATCase is our example of an allosteric. And we see this shape, which reminds you of hemoglobin. And what do you guess about the structure of ATCase? Is it one single subunit? No, it's multi-subunits. And so we see at lower concentrations, we have more difficult binding, and then as we bind in there, we get easier binding, and then up here we have a saturated enzyme. So again, we have the harder binding down at the bottom. Then we have a conformational change. And then we have harder binding, or we have a saturated enzyme up at the top. So hard binding, conformational change to easy binding, and then saturated. So again, these plots should remind you of myoglobin and hemoglobin. And what we're going to do is have two different models to explain these enzyme behaviors. We're going to look at the Michaelis-Menten kinetic model for our non-allosteric enzymes, and we're going to do that now. And next chapter, we're going to look at the models describing allosteric enzymes. We're not going to look at the math for those. We're just going to discuss those models. And that's next chapter. So let's dig in to our Michaelis-Menten kinetic models. Have you guys heard of this before? Anybody heard of Michaelis-Menten? You've heard of what class did you hear it in?
I just nutritional biology.
Oh, okay. So this is probably all repeat?
I like the same. Yeah,
Is it? Let me know how it's different. I'd like to know.
so far it's not.
Okay. So you're going to get an A, right? Why do you have to take a different one then?
The school I applied to said they preferred biochem. I don't know if they were like all about saying nutritional biochem, but it's the same.
Okay. All right. Well, I hope you enjoyed this class. If you have anything to add, yeah, this is a nice little break for you. All right. We're going to use explanations developed by guys named Michaelis and another guy named Menten in 1913. This is when this was developed. So that's so cool, right? We're going to use, and we still use, the math that was developed. And really, it's just algebra that we're going to be doing to explain this. And I just think I have an appreciation for scientists that worked back then because they didn't have the fancy things that we have upstairs, and or the support or the money that we have, and they did amazing things. 1913. I just love it. My grandmother was 13 years old. She taught in 1918, and she gave me her, before she passed away at 102, she gave me her textbooks that she taught physics and chemistry, high school physics and high school chemistry with. They're amazing. They're amazing to read. The chemistry textbook was broken up in elements, and the physics textbook, this was before quantum mechanics. You could almost feel the anticipation. Like they knew they didn't know everything, which I would say is a pretty good thing. When do you read a textbook and have them say, this is not the whole story? You just get that sense in the physics textbook. So I don't know. I have a sweet spot for these old-time scientists doing this amazing work that we still use today. All right. So the basis of this model, again, is that we're forming this enzyme substrate complex. What we're going to be doing over the next few slides is doing the derivation of the Michaelis-Menten equation. I am not going to have you do the derivation. I'm going to point out to you the things that are important through this derivation, but I'm going to derive it with you so that you can understand this stuff isn't that bad. You're going to be able to follow me. So over the next few slides, I'll tell you what's important for you to write down, but mostly just kind of stay with me and follow me. If I start to say things that you're not following, let me know. So the important basis is that we form this complex. Now, notice that, and this is very important too, that we have this is a reversible reaction. The enzyme coming together with the substrate forms this enzyme substrate complex. That going forward, we have a K1, or this is the rate constant for the formation, and this is K minus 1 is the rate constant for the breakdown. And then we have a K2 that's a rate constant for forming the product. So I need you to know that once you form this enzyme substrate complex, two things can happen. It can dissociate back into the free enzyme and substrate, or it can form the product. So that's one basis there. All right, so let's take a look at those rate constants. When you form the enzyme substrate complex, here is the rate law. And when you have the breakdown, here is the rate law. So what I'm doing in this top one, this one is this reaction, this forward reaction here. So that's what this is. So does everybody see this? This is the rate of forming this is the rate constant times the concentration of the reactants. Now, the rate of breakdown. Remember I said that there's two things that can happen. You can form the product, or you can break down into your free enzymes. So here, the rate of the breakdown is equal to this rate law plus this rate law. So the rate law for going forward to product and the rate law for going backwards. Now at equilibrium, the rate of forming and breaking it down is going to be equal. Right? At equilibrium, the rate of making our enzyme substrate complex and breaking it down is going to be equal. So what I'm doing here is setting the right-hand sides equal to each other. Now, go ahead.
I have kind of a dumb question.
No.
If the rate of formation of ES is the concentration of E times S, why at the top is it E plus S?
Oh, it is E times S. So this is, when we go back, let's go back to the kinetics. When you do the rate law, the rate of the reaction is the constant of the two reactants times each other.
Okay.
Okay?
Yep.
That's just the rate law. Well, that was a good question. The reason why this is plus here, because we're adding two different reactions here. So what we're doing here is adding those, or making those two equal. All right. Now, what we're going to do is we are going to substitute. So another word for equilibrium is steady state. So once equilibrium is reached, the concentration of free enzyme is the total minus the bound enzyme substrate complex. So what we're going to do is, this is the equation from the last one. So wherever we see free enzyme, we're going to put the total minus the ones that are with substrate. So here, I have it here, and that's it. So I put it in here, and then what we're going to do is divide both sides by ES and divide both sides by K1. This is just algebra, guys. I'm only doing algebra. So what I'm doing, take a look at this reaction, or this equation. This enzyme, I'm putting this side into here. So you see it right here? That is that right there. And then times substrate. And then what we're doing is dividing both sides by the ES, concentration of ES. So that's why this is down here. And then we're going to divide both sides by K1. So the K1 is gone from the left-hand side and now is divided on the other one. We're going to make this equal to our Michaelis constant. Now, what does that look like? These are the two rate constants for the breakdown, and this is the rate constant for the formation. So the rates of the breakdown over the rates of the formation is the Michaelis constant. So I want you to know the Michaelis constant is the rates of the breakdown over the rates of the formation. And what does it mean? If the rates of the breakdown are high compared to the rate of the formation, what do you think the affinity, likingness, of the enzyme is for the substrate? If it's going to be inverse. So the rate of the breakdown is bigger than the rate of the... Okay, what did I say before? I'm sorry. Let me go back. So the rate of the breakdown is greater than the rate of the constant. Then the affinity is low, but the Km is high. Okay? So it's an inverse relationship between affinity and the Km. I had a student in previous semesters that thought I was saying infinity and let it go for like 3 lectures. And she's like, what do you mean by infinity? Affinity, meaning likingness. Okay. So a a large Km means a low affinity. That's really important.
It's the affinity to make the
Enzyme. Yeah. So the Km describes how much the enzyme will bind the substrate, how easily, how much does it want it. Basically, how many bumps does it have to take? So you can imagine a substrate with a low affinity might have to go into the substrate like that, where one with a high affinity would just go like that. Does that make sense? Where it would just take maybe one collision of the substrate with the active site for it to be attached, to have that enzyme substrate complex. Where a low affinity might take a few times for it to bind. It's our way to describe these different substrates that might come into our enzyme. So it's a very important thing. So our Km, this is a great way to look at it, but this is how we calculate it. So we're going to calculate it. Now, what I'm going to do here, and over the next 2 slides, is sort of do some rearranging so that we can get some other terms. So here is what we had on the last slide, except I don't have the rate constant. So this was over here on the right, and this was over there on the left. And so what we're going to do now is multiply both sides by ES, right? Between this one and this one, I multiply both sides by ES. Now, what I'm going to do is bring this over to this side, right? I can do that, right? Add ES times S from here over to here. You guys follow that? Basic algebra. Okay. So now I have on the left-hand side, this one, and then over here. But then what I did is I took out the ES, so I'm left with the Km plus the S. Does everybody see how I went from here to here? If I see a lot of faces going, oh my God, this is not good. So here I took this, put it over there. But both of them have this ES, so I took it out. So what's left is the Km and that S. And then what we're going to do is divide both sides by what's in the parentheses, and I get this. So the enzyme substrate complex, that concentration, which is sort of hard to get, right? You can imagine, how do you get that concentration? Well, you can get it by taking the total enzyme concentration by the substrate concentration, whatever you're doing, divided by that Michaelis constant plus the substrate concentration. So that's how you know how much enzyme is with substrate. At initial stages, the rate of the formation of the product depends only on the rate of the breakdown because we have plenty of free enzyme. So our initial rate is only dependent upon the breakdown. So what we're going to do is we are substituting in, and we're using the rate. So we're doing this. We're multiplying both. So this ES equals this stuff. We're putting K2 on both sides. So this is the rate of making the product. And that, we say, is the initial rate. And when the substrate concentration is so large that the enzyme is saturated, so here is at the saturation point, we have Vmax. And that's just not yet. You don't need to know anything yet. So far, you don't need to know anything. But I need to know, there's one concept I need you to know, that the initial rate depends on the breakdown or formation of the enzyme substrate product because there's so much free enzyme. But at maximum, or when we're at saturation, it depends on the total enzyme concentration. Remember, at the low concentrations, not all the spots are full. So we need to know the concentration of that enzyme substrate complex in order to figure out how much is going to be made. But at the high concentrations, all enzymes are filled. Now, if we put Vmax into the K2 ET from here, if we take Vmax and wherever we see this, this is our Michaelis-Menten equation. The initial rate is equal to the maximum rate times the substrate concentration divided by the Km plus the substrate. I know this seems unusable, but what we're going to do on Friday is make it a usable form. We're going to make it a usable form. But there's a couple things that I need you to understand. Here, you see more plainly the inverse relationship between rate and the Michaelis constant through this equation. I am not going to ask you to memorize this equation, but I want you to know relationships. That there's an inverse relationship between the rate, V is rate, V velocity is rate. So between the rate and the Michaelis constant, and in order to get what that Michaelis constant is, we figure out the substrate concentration that it's equal to. So we just put in S, and we figure out that it's Vmax divided by 2. Let's take a look at this just for a minute, and then I'll stop. It's Vmax divided by 2. So what we're doing, and I mentioned before, the Km is the substrate concentration where the Vmax is divided by 2. Let me use my pen, and then we're going to take our quiz before we leave. All right, so what if we had something that had a high affinity? You would think that it would go like this, right? That you would have the rate would go up quickly, right? So this is, stop it. Let's just do HI for high, and then L for low, okay? Because every time I do something, it is not good. Now, we get the same Vmax, but imagine we have these three. This is normal, this is a high affinity, this is a low affinity. Take a look at what's happening to the Km. When we have a high affinity, this value is staying the same. What substrate concentration do we have for Km? A low one. Does everybody see that? At this Vmax, you're doing a line across, right? So normal, we have this value. But what we have here is the Vmax, you come over and you go down, and that substrate concentration is very low. So for high concentration, or high affinity, I mean, we have a low substrate concentration or a low Km. For a low affinity, we have a high substrate concentration for our Km. So that shows you the inverse relationship. Now, it's kind of a pain in the butt to do an experiment like this. Why would this be painful? Those of you that have ever done any lab work will know when you have a plot, and I'll draw it right here. And I do, all of these are just different experiments. So here I do an experiment, 100 chymotrypsins and low substrate concentration. And I look at the initial rate. And another one, and another one, another experiment, another experiment, another experiment, another experiment, another experiment, and another experiment, another experiment. Am I at Vmax? I don't know. Am I at Vmax? I don't know. Oh, it's a pain. Whenever you have a hyperbolic plot, scientists hate it. What kind of plots do scientists like? Linear, all right? So what we're going to talk about on Friday is how to make the plots linear. There will be no quiz, but right now we won't have our quiz. And you can just pass them in.